Alright, so today I'm going to be explaining another important article with the title Fast Graph Attention Networks Using Effective Resistance-Based Graph Sparsification. Again, this effective resistance is a very powerful tool for capturing some global topological features. But now they use it for graph sparsification. You can use it for hierarchical graph pooling. Write a paper about this and apply it for hierarchical graph pooling, and then do some experiments on some benchmarks, and then submit it to a conference. This is a valuable work. Because traditionally effective resistance, this topic is in spectral graph theory. People in some universities, some computer science department focus on that, but they work on spectral graph theory, not machine learning. So this is a multidisciplinary research area that is less understood. It should be integrated with machine learning more than before. But one of the reasons that it is not integrated is because to solve this, you need to have inverse of pseudo-Laplacian, or you should solve a system of linear equations. Spielsman in 27, proposed that popular article about that. But so let's carry on to see the importance of this paper in 2020. The attention mechanism has demonstrated superior performance for inference over nodes in graph neural networks. However, they result in a high dimensional burden during both training and inference. So, we propose fast graph attention method to make attention-based GNNs lightweight by using spectral sparsification to generate an optimal pruning of input graph. This results in a per epoch time that is almost linear in the number of graphs as opposed to quadratic. So we theoretically prove that spectral sparsification preserves the features computed by graph attention model, thereby justifying our fast graph attention. And also they show that it's 10 times faster, better computational time and memory requirements, and allowing usage for large graphs as well. So generally, GNNs rely on graph convolutions. So this is G is the graph convolution. And U here is the matrix of eigenvectors. So a single neural network is defined like this. This is the preliminary thing that you know. But they propose fast graph attention network, which is an edge sampling based method that leverages effective resistances of edges to make attention-based GNNs lightweight. The effective resistance measures importance of the edges in terms of preserving the graph connectivity. Fast graph attention uses this measure to prune the input graph and generate a randomized subgraph with far fewer edges. So they provide theoretical justification of using this spectral sparsification in the context of attention-based GNNs. So it has related work to graph sparsification, accelerating graph-based, graph sparsification, neural networks. So what is this idea? In graph attention, we have attention coefficients. For example, if I is the source node, J is the target node. So source and target is defined like this. So the neighbors of J are these nodes. So we can find the attention coefficient for all of the edges that are neighbors of this J's node. Now that we have obtained them, so H sub I can be written as linear combinations of J's in the neighbors. Of course, my notation is the opposite. So this is I and this is J. And so we have a representation of each node. But it's computationally expensive. You cannot do it, especially for many layers. So we propose to use edge sampling function that sparsify graphs by removing non-essential edges. This leads to direct reduction in the number of attention coefficients to be computed. So edge sample denotes a randomized sampling function, and given an edge set, adjacency matrix, and a number of edges to be sampled, Q returns a subset of the original edge set. So it's a sampling. We sample edges. So sample a graph, the computed gamma, and then once we compute gamma, then we can update it using this simple equation. Then we concatenate and compute the loss. This is the fast graph attention. So the critical step is this edge sampling. And we know that if we sample and sparsify, then the spectral graph sparsifications is sandwiched between the upper bound and the lower bound by plus and minus epsilon. So what is effective resistance? It's just the reason that it's computation expensive is because of this L, which is the pseudo-inverse of graph Laplace. And how do you want to do it efficiently if you have a big graph? Even in your brain, I don't think your brain does any kind of pseudo-inverse. So you see it's not bio-inspired. It has many problems. That's why people nowadays have alternative measures for global topology. But let's look at this definition. Of course, I have a playlist for effective resistance and random walks. So because this is very popular, so I assume everyone knows about this effective resistance thing. So just let's look at the algorithm for effective resistance-based sample edge function. We sample an edge from distribution P sub E proportional to the random walk. So this is critical because our distribution, when you want to sample an edge EI, you look at this effective resistance of this edge E. And proportional to that you sample, so you got the idea. Then you add the weights and add the edges to the quotient one, and once you do sampling, you get your quotient graph. But can preserving the spectral structure of the graph lead to good performance under the GATT model? And so they proved some theorems that yes, there is an upper bound, and for example, they propose cosine similarity where the attention mechanism is this. Also, another definition in 2018, they call it GAN, gated attention network, which defines attention like this. It's a gated attention. So this is a fully connected layers, and J is in the neighbors of ith node. So we can compare it for different data sets, the fun micro score. So fast GATT can significantly reduce the computational time. across multiple datasets.